Having talked about magnetic forces on moving charges, we naturally lead into magnetic forces on currents. Consider these two important facts. Magnetic fields exert forces on moving charges, and a current is the movement of charge. So clearly, magnetic fields will exert forces on currents as well. In principle, you could simply treat this using F equals QV cross B, in other words, just figure out how much charge is moving in the current. But pragmatically, it will be useful to find some relations between the magnetic field and the current itself directly. Consider a wire in a magnetic field, where the wire is perpendicular to the field, and the field in this case is going into our page. If we direct a current from the bottom to the top, as it passes through this region of length L of magnetic field, this is magic magnetic field, where there's no field outside this region and just this field inside, then we can say by right-hand rule that the V here, because current is moving up like this, so this charge is moving this way, crossed into the field, which is inside, would give us a force pointing leftward. Notice here, of course, that this is an external magnetic field, not the field generated by the wire, which, of course, would be circular rather than planar like that. Let's think about how we might increase the QV cross B force. Well, if we increase the magnetic field, we would expect the force to increase, of course. And if we increase if we increase the current, we either are transporting more charge, which increases Q, or transporting it faster, increasing V. That's the only way to get a higher current. One or both of those things must be true. And in either case, if we increase Q or increase V, we increase the force. And then finally, if we have a longer wire, there will be more charge total being affected, so we'd expect the force to increase as well. In other words, we capture more charge in the field. All of this can be put together in a formula, which is that the force is IL cross B, where here we're cheating a little and we're making I into a current, into a vector. Usually I is considered a scalar. It's the amount of charge passing through a point where we've put a little gate per second. Here we're going to say, well, if we were to take a current, we would make a vector where the vector points in the direction the current flows and has a magnitude equal to the current, then we'd have this vector. This form is vectorially consistent, which is nice. It fits the right-hand rules that we've known. You don't tend to see people use it that much. Instead, you tend to see people just write out the magnitude of the force and then get the direction with the right-hand rule. So the magnitude would be ILB sine theta, which is the generic result for cross product. It's the first times the second times the sine of the angle between them. And then it just turns out that the problems people tend to write, for no particularly good reason, tends to have the field perpendicular to the current. So you mostly remember this as the force is ILB, the current times the length times the magnetic field. The right-hand rule here works for conventional current. Conventional current, where the positive moving. For real current with electrons, you'd need to flip the direction of F. As an aside, we can now see the definition of the Tesla in terms of base SI units. 1 Tesla is 1 Newton per amp meter. The fact that the Newton and the amp and the meter are all human scaled means that the Tesla will not be human scaled. There's just no way around it. That's the way nature works. Fields of 1 Tesla will just be large fields, at least for the human scale. All right, so which of these wires feels a force directed to the left? We, of course, should just do right-hand rule. So we have, in case A, we have rightward crossed into the board, which would be upward. And then flipping the direction means, of course, we've just flipped the sign, so that's not going to help us there. If we have upward crossed into the board, we actually do get the leftward. And then, of course, if we flip the I again, we get the flip of the force by flipping one vector. Flipping one vector will do it, whichever one we flipped. All right, so in the setup shown, which way will the wire be pulled by magnetic forces? What we have here is a standard so-called C magnet, relatively strong one, which you can't tell by looking at it, but turns out is a relatively strong one, whose north and south have been marked. And then we're going to have a current, and the current is going to flow. current happens to flow from the apparatus, you'll see as he sets it up, it flows up here, down this wire, across the yellow this way, and then up again. So during this time, the magnetic field is pretty contained within that area, and the current is flowing that way. And the question is, which way will the wire be pulled? And I'm about to let it play and you'll be able to watch it, but right now you should be able to actually come up with a thought even as we get started.
In this demonstration, I have a length of wire suspended between the poles of this strong magnet. We have the north pole here and the south pole here, and I have this apparatus connected to a high current source. Now when I close this switch, current will flow down this wire, along here, back up, and then back to the power supply. So the current will be flowing along the wire this way. Question is, when I close the switch, which way will the wire move? Will the wire move out, away from me? Will it move back towards me? Will it be attracted to the North Pole? Will it be attracted to the South Pole? Or will it stay in place? So as you can see, when I sent current through the wire, it moved back towards me. And because we're dealing with current moving in a wire and a magnetic field, we can use the right-hand rule to figure out which way the wire should move. So if the current is flowing this way and the field is going down like this, if we curl our fingers, then it shows that the wire should move back. Now, if I reverse the current going through the wire, now the current is going this way, the field is down. If I curl my fingers, we can see that it curls out away from me, and if I close the switch, the wire moves out of the magnet.
You also see there's a fair bit of inertia, so it actually oscillates around that point. It moves out and then swings back a little bit, but does oscillate around the point he was talking about. So, currents feel forces from magnetic fields, but currents also generate magnetic fields. This means that two currents will interact via the forces transmitted by the magnetic fields they create. And this just illustrates the way it would go. If we have this current, and we just consider what field this current generates, it generates a circular current, right? Something which is looping a field which is looping around like this, and so on. All different, not that it's growing like that, but all different sizes. If we then bring another current in, and on the right-hand side, the field is always heading inward, so we have something heading upward, and we cross it into something going inward. We have current flowing that way, and we have magnetic field going into the page. Then we can see from the right-hand rule that the output will be that way, which means that the new current is going to be attracted to the original current. By the way, of course, if you do the same exercise over on the other side, the field due to 2 will be into the page, right? As it goes around, it will be coming out of the page. It would be these dots all the time. So over here we would have the current moving upward, the field is coming out of the page, and now the cross product points that way. And not surprisingly, it also feels an attractive force, and by third law, those two forces would have to be the same. So physics still works on the mechanical level, even as we bring in electrodynamics. All right. If the currents were anti-parallel, the forces would have been repulsive. And you should be able to convince yourself of that as well. So we have here that currents that are in the same direction attract, and currents that are in opposite directions repel. Be careful, because we're going to use the idea in electromagnetism that opposites attract and like things repel, but for currents it's the reverse of that. So just be aware of it. Just don't think that it's always the case that what you learned in middle school must be true. Let's find the force between the two currents, and I'm going to make some concreteness. So I'll say two currents that we're going through a region where they both have length L. In this case they're parallel, so they'll attract. We'll say they're separated by a distance r, and they have magnitudes I1 and I2. So let's look at what I2 2 does what current 2 does on current 1? Well, it produces a magnetic field, and we know that this magnetic field will be coming out. So the field from 2 is going to be everywhere the same and out of the page. And then, of course, when we have something going like that, that will produce a force which is attractive, as we said before. The size of the magnetic field we did earlier, the size that 2 creates at 1, in other words, the field strength that 2 creates here, is mu naught I2 over 2 pi r. So hopefully you remember that from when we talked about field strengths a couple of days ago. And that will attract wire 1 with a force which is I1 times L times that field. So we end up that the force of 2 on 1 is mu naught times I1 times I2 times the length over 2 pi r. And of course you can see immediately that if you swapped and said, well, what is the force of 1 on 2? You'd just change the order of I2 and I1, which wouldn't change anything by third law. Is this a thing you should memorize? Almost certainly not. It's a thing you should roughly keep in mind, that it's the product of the currents that matter. Probably a good thing to keep in mind. All right, 3 long wires all have the same magnitude current. There is no force on wire Y. The distance between adjacent wires is the same. 3 students are discussing this situation. Anita says, for the force on Y to cancel, the currents in X and Z must be in opposite directions. Beatrice says, no, for the forces on Y to cancel, the currents in X and Y must be in the same direction, but opposite as the current in Y. And Carol says, no, for the forces on Y to cancel, all we care about is that the current in X and Z are in the same direction. Which of these students is correct? Well, let's assume if X and Z were in opposite directions, then their effect on Y, let's say that X and Y are both out of the board. So out of the board, into the board. Then the effect of Y from X would be to be attracted, and the effect from Z would be to repel, and that force can't cancel out. So Anita can't be right. Let's instead say that X is out of the board, Z is out of the board, but Y is into the board. In that case, the force from X repels, the force from Z repels the other way, and that can cancel. So Beatrice is certainly not obviously wrong. But then we can test Carol and say, well, what if this had been outward as well? Then it would be X would attract, and Z would attract, and it would cancel again. So it turns out that as long as X and Z have the same direction, it doesn't matter which way Y is going, i.e., Carol was correct. All right, if we were to take the long wires and bend them into loops, the same sort of behavior occurs. Currents in the same sense attract, and currents in opposite senses repel. Because you could sort of take each little segment of the bent thing and see how it looks in the field of the other one. This sets up an analogy between current loops and permanent bar magnets because they have fields that look very, very similar. You might remember that for bar magnets, we had stuff coming out and looping around and coming in, coming out, looping around, coming in, etc. And we at least made an argument that these are actually going to continue through, and so you really just have a loop of current, a loop of field, and so on, with the weirdness that this guy must wrap around to being that guy. And that looks a lot like the field that's going through the current loop. So there's at least some analogy between the two. We can pretend that the current loop is actually a magnetic dipole. And later on we'll say it actually is a magnetic dipole. It looks like there's a bar magnet there. By the way, these are mythical things. But we do see that the north end and the south end attract, and the north end and north end repel. This will end up being useful when we start investigating the microscopic origins of magnetism. And then finally, one kind of weird application of this is something called the magnetohydrodynamic drive. Very fancy words in physics, of course, and what we can see that's going on here is we have two things. We have magnetism, and we have hydrodynamics. This is a proposed propulsion system that could create thrust without any moving parts. And the way it does that is we have a fluid in a tube, and we run a high voltage across that tube, which generates a current running through it. So now there's a current going downward, but we've sandwiched it between two powerful magnets so as to create a magnetic field to the right, and so it's relatively easy to see that the force would be out of the page. That would tend to move the water, or whatever you're running the current through, out of the page. But then the corresponding Newton's third law says that means the whole other system, the thing generating a magnetic field, must be getting a backward pulse, and so therefore backward impulse. So it would tend to thrust this into the page. This is something called, in the book and film called The Hunt for Red October, they called it the caterpillar drive. It was proposed in the 80s that it might be used in submarines because it would be very, very, very quiet. There are no moving parts. There's no fan or turbine blades or pumps going or anything like that. It has turned out to be really hard to do efficiently, so there are some proof of concept models out there, but it's not been turned into workable real drive yet, although the main thing is generating the magnetic field, and if superconductors become cheap enough, that should be easy, and then it might become worth doing. More pragmatically, the same sort of system is used to move around coolant in nuclear reactors. In nuclear reactors, you really would like the idea of having few moving parts because those are more reliable. You don't like your pump to break down in the middle of cooling your reactor. And so they get molten sodium, which is crazy, but they make a current, which is a river of melted sodium. It's very easy to pass current through that, electric current through that, because it's a conductor. And so they're able to kind of sloth this coolant through, push it through the system where it can interact and pick up heat. Why is it molten? Because nuclear reactors run really, really hot, and they melt the otherwise solid sodium.